The compass is one of the single most important tools in the navigator's toolbox. Unfortunately for mariners, our magnetic compass is subject to two significant errors: magnetic variation and compass deviation. Thankfully, we can calculate these two errors, and the difference between a compass course or bearing and a true course or bearing is the sum of variation and deviation. The navigator must convert the course they have steered by compass into a true course in order to plot it on the chart, and conversely, a true course measured on the chart must be converted to a compass course to steer by. Let's take a look at variation first. Using a compass, we measure direction clockwise from true north using 360 degrees notation, and our charts are oriented to true north. However, our magnetic compass points to magnetic north, which is slightly different to true north. This difference changes from year to year and according to your position. As true north is where charts are lined up on, all the lines of longitude run up to the true North Pole. The direction in which the compass needle points is known as magnetic north. Magnetic variation is the result of the Earth's magnetic field not being precisely aligned with its geographic axis running through the poles, which means that, depending on where you are, your compass needle might point east or west of true north. The compass needle is attracted by the magnetic force produced in the outer liquid part of the Earth's core, which varies in different parts of the world and is constantly changing. As of 2020, the Earth's magnetic North Pole is within the Arctic Ocean and not far from the international dateline, a few hundred miles from the true North Pole. It is moving away from Canada and towards Siberia. So, magnetic variation changes with position and time. Magnetic variation in the British Isles ranges from 0.5 degrees east in Lowestoft to 4 degrees west in parts of Northern Ireland, the Outer Hebrides, and on the west coast of Scotland. A small part of the UK benefits from zero variation. In fact, there's some concern in the scientific community that we are about to suffer a magnetic reversal, when, over a period of a few thousand years, the Earth's magnetic field will weaken considerably, and eventually our compass needles will point roughly towards the south geographic pole. Scientists know that this has happened many times in antiquity, and apparently one is well overdue. But let's not worry too much about that for now. The angular difference between true and magnetic north is called variation. And as we see here, the variation can be either east or west of true north, depending on your position. And here you can see how variation can change across the globe depending on your position. So, how do we know what the variation is in the area where we are sailing? Local variation is indicated on the compass rose. Look at RYA Training Chart 3. Each compass rose shows the variation for that area. Let's look at this one just north of Dawson Bay. The variation is shown on the compass rose as being 7 degrees 25 minutes west, and we are told that this was calculated in 2005. In addition to variation changing with position, it also changes over time. This is because the position of the magnetic North Pole moves in a small circle around the true North Pole over hundreds of years. This annual change is indicated by the figure in brackets. On Chart 3, it is 8 minutes east annually. This means that the variation is decreasing by 8 minutes each year. That is, the variation is westerly, but as the magnetic pole is moving in an easterly direction, we deduct 8 minutes for each year since 2005 until our current date. So, to repeat, to find the variation for any given year, we need the variation from the compass rose and the year for which it was correct. Then add or subtract the annual change. In this case, because the variation is west and the change is to the east, we should subtract the annual change. Here's an example. What was the variation at this location in 2007? Variation is 7 degrees 25 minutes west in 2005. The change is 16 minutes east, that is 2 years at 8 minutes per year. So the variation is 7 degrees 09 minutes west in 2007. This would be rounded up or down to the nearest whole degree for practical use. So the variation to use in 2007 is 7 degrees west. Obviously, this will be different for each additional year, and you will take account of the date when calculating the change in variation. Let's do another. What would the variation at this location be in 2018? From 2005 to 2018 is 13 years, and the variation is changing at 8 minutes per year, so a total of 104 minutes. Using base 60 arithmetic, this gives us 1 degree and 44 minutes, and deducting this from 7 degrees 25 minutes, we get a variation of 5 degrees 41 minutes west in 2018. Of course, in practice, we cannot measure within a degree, and much less so steer a course to this level of precision. So, in 2018, we would round this to the nearest degree, which is 6 degrees west. If you look at the other compass roses on RYA Training Chart 3, you'll see that the variation changes as we move south. In reality, the general variation will not change this much over an area of this size, and has been exaggerated on the RYA Training Chart for exercise purposes. However, it is possible to get considerable changes in local variation over short distances. If we take a look at this section of the chart in the area north of Diamond Reef, you'll see an area delineated by a squiggly line, with plus or minus 15 degrees written in its middle. This is an area of local magnetic anomaly, where your magnetic compass might suffer a random error of 15 degrees either way. Such anomalies are usually the result of large deposits of iron ore in the Earth's crust. A note of caution is included in page 68 of the Training Almanac. As each of you will be taking this course and the exam at different times, and yet the answers to questions have to use the same data, all of the exercises in this RYA Day Skipper theory course that include variation are based on 6 degrees west. Don't worry, you don't have to remember that. It will tell you the figure in any question where it's required. The effect of variation is the same for all boats in the same area at the same time. Deviation, however, is specific to the boat and the course it is sailing on. Deviation is caused by electromagnetic fields from electrical equipment or ferrous metals in the vicinity of your boat's compass, which affect the accuracy of your compass reading. The red mark indicates the point of greatest magnetic influence, probably the engine, which is influencing the boat's compass. As the boat changes course, the relative positions of the magnetic influence and the boat's compass change too, and so does the value of deviation on that heading. Compass deviation is not a problem provided that the error for each heading is known and allowed for. Your boat's compass can be checked and corrected by a compass adjuster to measure the deviation, and altering the positions of the magnets built into a compass can reduce the errors to manageable figures. A vessel's deviation is recorded on her deviation card and is normally plotted as a graph. Take a look at the example of a deviation curve given inside the back cover of your RYA Training Almanac. Of course, you'll never find a curve in a real almanac, because each vessel has its own unique curve. The easiest way to check for changes to deviation is to position your boat so that you are heading down a fixed transit. Find two objects marked on the chart that are in line with each other. Measure the true bearing to the transit from your chart. Add or subtract local variation to get the magnetic bearing, and compare this to the compass bearing. Any difference is deviation. If the magnetic bearing is less, then the deviation is west. If it's positive, then the deviation is east. We'll talk more about knowing whether to add or subtract variation and deviation in a moment. Electrical circuits, radios, instruments, and chart plotters can all cause deviation. And the problem with this type of cause is that it can come and go as equipment is powered up and down. So these types of equipment should be located well away from the compass. However, as we see here, that's not always the case on boats loaded with electronic navigation equipment. And all of this is pretty futile anyway if you inadvertently bring objects such as tools, sailing knives, and especially anything containing magnets close to the compass. Your hand-bearing compass is also subject to deviation. However, it's impossible to create a deviation card for it because it could be used anywhere on deck, with varying degrees of deviation at each position. So it's important that the navigator taking bearings positions themselves well away from objects containing ferrous metals, radios, loudspeakers, etc., and that they don't have a mobile phone in their pocket close to the hand-bearing compass. Another common mistake when sailing at night is to be shining your head torch down into the compass. The close proximity of the torch's batteries will affect the compass. At day skipper level, whilst you need to be aware of the existence of compass deviation, you are not expected to allow for it in your chart work. However, you must take account of variation whenever you measure a bearing with a compass and want to plot a corresponding position line on the chart, or when you calculate a course to steer and need to give an instruction to the person who is steering. Imagine we're in the RYA training world, where magnetic variation is 6 degrees west of true north, and that you've used the hand-bearing compass to measure the bearing from your vessel to this isolated danger mark, with a reading of 237 degrees. If we simply dialed 237 degrees into our chart plotter and plotted a position line, it would be 6 degrees out. To get it right, we have to subtract the 6 degrees of variation before we plot our position line. Thus, 237 minus 6 is 231 degrees, which we can draw on the chart. Let's look at this in a little more detail. Imagine we have measured a bearing of 135 degrees. Again, this is relative to magnetic north, so we would say 135 degrees magnetic. Or, if we were writing it down, we would add a capital M suffix. This is 135 degrees from magnetic north. So if, for example, the magnetic variation was 6 degrees west, then the true bearing would be 135 minus 6, which equals 129 degrees, true. So the rule is, when variation is west and we are going from compass to true, we subtract variation. Notice that we've added a T suffix, and from now on you should get into the habit of suffixing bearings or courses with either M or T according to whether they are magnetic or true. If, on the other hand, we were sailing in Sydney, Australia, where magnetic variation is 12 degrees east, then we'd need to add the variation for the compass bearing to arrive at a true bearing. The rule is, when variation is east and we're going from compass to true, we add variation. Until now, we've concentrated on converting from magnetic to true, the flip side of which is true to magnetic, such as when we plot a course on our chart and need to instruct the person steering to steer a course according to the magnetic compass in front of them. If the course we need is 045 degrees true and variation is 7 degrees west, then we need to add variation in order to come up with a magnetic course. The rule is, when variation is west and we are going from true to compass, we add variation. Finally, if variation is east and we are going from true to compass, we subtract variation. So you can see that sometimes you add the variation and sometimes you subtract it. If you struggle to remember whether to add or subtract, remember the cadet mnemonic. From compass to true, you add easterly errors, and therefore subtract westerly errors. And in reverse, to go from true to compass, you add west and subtract easterly errors. Hopefully, to not add any further confusion, another way you might like to remember this is error west, compass best. Error east, compass least. And by that we mean if the variation is west, the compass is a higher number because we subtract to arrive at true. And if variation is east, the compass is a lower number because we add east to arrive at true. By best we mean a higher number, and by least we mean, of course, lower. And a final mnemonic to help you remember the order of working. To convert a compass bearing to true, first add or subtract deviation to obtain the magnetic bearing, then add or subtract variation to obtain the true bearing. The quickest and easiest way to fix your position is to note the time and log as you pass a charted object. Buoys are the obvious choice, but be aware that they can be relocated, especially in areas of shifting sand or mud banks. Keep your charts up to date, and where possible, choose an object firmly fixed to the seabed. Make a note on your chart as you're alongside or near the object, and as easy as that, your position is fixed. If no object is close by, we can take a bearing on an identified charted feature that we can see. When the bearing of a known object is plotted onto a chart, it is called a position line, and the observer's boat must lie somewhere along it at some point. The bearing line drawn to the object represents our line of sight, and therefore we know we are somewhere along this line, but not exactly where. If we identify and plot a second position line, the intersection of these lines should mark our position at the time the bearings were taken. There's only one place where you can possibly be on both position lines, and that is where they cross. If you have measured and plotted the bearings with precision accuracy, then your position would be exactly where those position lines intersect. However, in the real world, on a moving boat, we are rarely able to achieve such precise results. In fact, it's normal to add another bearing to a third object to our plot, and this then becomes known as a three-point fix. This third position line doesn't increase the accuracy of our fix, but it helps to guard against any errors such as a bearing being wrongly read or plotted. Unless you have a stationary boat and very steady hands, the lines are unlikely to intersect perfectly, instead coming together in a triangle called a cocked hat. Your true position could be anywhere within this triangle, so the smaller it is, the more accurate your fix. The wary navigator will always presume that the position is closest to the nearest hazard. The perfect three-point fix would involve 3 landmarks that are spread out at 120 degrees apart, thus splitting a circle equally. But it's rare to be able to identify objects spread in this way in real life. Any charted feature can be used to take a visual bearing. Lighthouses, radio masts, and buildings are the ideal choice as they don't move and are easy to sight through the compass. Headlands can be good, but shallow promontories are harder to accurately sight than steep cliffs. Buoys can also be used, but be aware that they can move on the tide. However, they are often readily available and easy to identify, and may be much closer than a distant landmark. And even if a buoy is 20 meters out of position, a bearing taken on it is likely to be more accurate than one taken on a lighthouse that is just within your range of visibility. However, you should avoid taking bearings on objects that are too close together, or the angle of intersection could lead to a large area of uncertainty in your fix, as seen here. Once you've chosen the charted objects to take your three-point fix, you need to take your bearings as quickly but carefully as possible. Note them down as you go and leave the one most abeam until last. This bearing changes the fastest. Convert the bearings from magnetic to true and then plot them on the chart. You're unlikely not to have at least a rough idea of where you are. So in fact you only need to draw part of the first line in the vicinity of where you expect the fix to be, and the second and third lines can be even shorter again. Mark the position with the symbol for a fix and write the time and log reading next to it. We could also fix our position with a single position line and a depth reading. Here we know again that we are somewhere along the position line that we have plotted. In this instance, if we monitor our depth till we are crossing the 20-meter contour, then take a bearing on the belfry, our current position would be where the position line and contour line intersect. Of course, we must add the current height of tide to the 20-meter contour depth. So in this case, if the height of tide was 2.2 meters, when our depth sounder was showing a depth of 22.2 meters, we know we are passing over the 20-meter contour. Or we could use a transit and a bearing. A transit is where two objects are in line with each other, and offers a very quick and accurate method of establishing a position line. There's no need to adjust for variation, and there can be no error in reading the bearing. In this case, the green buoy and the elevation beacon at the top of Beacon Hill are in line with each other when viewed from our current position. In theory, we don't need to measure the bearing with our hand-bearing compass. We can simply draw a line through each charted object to establish your position line. However, it's good practice to check the bearing of the transit, just in case we've got the wrong buoy. If we observe that the objects are lined up with each other from our current position, then we must be somewhere on that line. If we then add another position line, we can fix our current position. We'll look again at transits and visually fixing your position in the lesson on pilotage. And we'll learn how to fix our position using GPS in the lesson on electronic navigation. Another quiz for you. Remember, if all else fails, your vessel's old-fashioned magnetic compass, along with a mechanical or Dutchman's log, lead line and charts will enable you to navigate safely without any electronic gizmos. and there's a great deal of satisfaction to be gained from safely navigating using the traditional skills you're learning now. Well done! You've completed this lesson. Now attempt exercise F.